feature designed to identify the second largest integer with a predefined array, while finding maximum value is straightforward. Finding the second largest requires more non-select logic. The program must track two distant value simultaneously and ensure that duplicate of the primary largest value don't accidentally get flagged as the second largest. This ensures data integrity when analyzing a list of code or numerical value. For looping, I use a BEQ branch if equal instruction as a loop termination. By comparing a loop counter $T0 against the array size $T1, the program knows exactly when to stop. Branching. The core logic resides in conditional branches like BGT branch if greater than. If the current element is larger than our current max, we branch to an update routine. If it's not larger than a max, but larger than the second max, we use another branch to update the second value. We also use branch BEQ to skip the element if it's exactly equal to current largest, effectively handling duplicated values. Input processing and storage. For the implementation, the input is stored in the data statement. This storage, the array myArray is defined using .word directive which allocate 32 bit space for each integer. Processing to process the data, the program uses the LA.address instruction to point to the start of the array and the LW.word instruction inside the loop to put each individual value into the register for compression. So what happens inside the hardware? To understand how this runs, we have to look at the instruction between the CPU and the memory. The register $T0 acts as the loop counter. $T6 and $T7, these are the largest and the second largest order. They are initialized to the smallest possible integer to ensure any possible number in the array will be larger than initial state. $A0 used for system calls will load the address or our string, message or the final result into $A0 so the OS can print them consoling. The text segment hold the actual machine code. Execute the floor sequence until it hits a branch or jump. For example, when the BGT condition is met, the text segment execute jump forward to the update largest block, then jump back to the next inter block to continue the sequence. The data segment is where our array and our string message reside. When we call LW $T3, $T5, the CPU reaches into the data segment at the specific memory address, calculate to retrieve the value. For the visual demonstration, look at the sample output. We can see the program running correctly. Input array 12, 35, 1, 10, 34, I. The program identifies 35 as the largest. It correctly identifies 34 as the second largest. The console output clearly displays the second largest number is 34, followed by clean exit.
Good day to my lecturer and everyone. My name is Nurul Fatini binti Sharul Nizar, and today I will be presenting my individual feature for the Board Security System project developed using MIPS assembly language. My specific focus is on the feature display only code codes. As shown in the agenda, we will cover everything from objectives to the final implementation. So the next slide is introduction. It is designed to scan and filter vault security code based on their numerical parity. A key distinction here is that the process evaluates the actual data value stored within the array rather than just filtering based on the index position. This ensures we are auditing the codes themselves. Alright, we have 4 primary technical objectives. Number 1, to perform memory traversal using 4 byte offsets. Number 2, to implement bitwise logic using the ND instruction to determine parity. Number 3, to apply conditional branching with BEQ for data filtering. And the last one is to manage hardware registers effectively for data loading and loop counting. Let's look at the logic flow. We begin by initializing pointers, loading the base address of our array into $S0. During the array traversal loop, the system fetch each 32-bit integer using the LW load word instruction. So the most critical part is the parity analysis. We execute a bitwise AND operation between the value and the immediate value 1. If the least significant bit is 1, the code is identified as code and sent to output. So, processing via system calls, if it's 0, the value is bypassed. We then increment the pointer by 4 bytes to move to the next memory slot. This slide is MIPS assembly implementation that I get. It is important to note the difference between index-based and value-based filtering. While index-based checks if the position is odd, my feature performs value-based filtering. This means we check if the security code itself is odd. This distinction is crucial for accurate data auditing within a high security code system. As you can see in the sample output from the Mars simulator, the system correctly identifies and displays only the odd codes 21, 43, and 65 from the sample data provided, finishing the execution smoothly. This slide shows to achieve this, I utilized core mix instructions such as LA for addressing, LW for data retrieval, and ND for parity checking. So, in conclusion, this project successfully demonstrates how MIPS logic and effective memory management can be integrated to filter data at the hardware level. It effectively bridges the gap between high-level logic and computer architecture. Thank you for your time. That's it.
Hi, my name is Nur Sabina binti Azzi, and today I'm going to talk about my individual feature implementation for the computer organization and architecture course using MIPS assembly language. My selected features is display code at even or odd index positions. This feature displays security codes stored in an array based on whether their index position is even or odd. In MIPS, array indexing starts from 0, therefore even index positions are 0, 2, 4, 6, and 8, while odd index positions are 1, 3, 5, 7, and 9. The objective of this feature are to practice array traversal using loops, to apply branching instruction in MIPS assembly, to distinguish between even and odd index positions, and to control output display based on logical conditions. This feature focuses on understanding how data is processed at the hardware and instruction level, which is a core concept in computer organization and architecture. First, the security codes are stored in an integer array, the data segment. An index counter is initialized starting from 0. A loop is used to traverse the array until the last element is reached. For each iteration, the index value is checked to determine whether it is even or odd using a modulo operation. If the index matches the selected conditions, either even or odd, the corresponding code is displayed. Otherwise, the program skips that value and continues looping. How input is processed and stored. The input values are stored sequentially in memory inside the data segment. Each integer occupies 4 bytes, and the base address of the array is loaded into a register. The address is incremented by 4 bytes for each loop iteration to access the next array element. This demonstrates how memory addressing and array traversal work in MIPS assembly. In the text segment, instructions are executed sequentially starting from the main level. A loop is created using a branch instructions that checks whether the index has reached the end of the array. If the condition is not met, the program jumps back to the loop level. Branch instructions such as PEQ and PNE are used to control whether a code is displayed or skipped. Data segment. The data segment stores the integer array containing the security codes. It also contains a string message used for output display. These values remain unchanged during execution, while the text segment instruction manipulate and access them using memory address. Looping is implemented using a combination of increment instructions and branch instructions. Branching is used to compare the modulo result with 0 to determine even or odd index positions. For example, if the index is even, the program displays the code. If the index is odd, the program branches to skip the output. I'll explain about what happened inside the register during execution. The register S0 stores the base address of the array. This register is used to keep track of the current array element. The register T0 acts as the index counter, starting from 0 and increasing by 1 for each loop iteration. The register T2 stores the result of the modulo operation used to check whether the index is even or odd. The register A0 is used to pass data to the system call for output display. The program counter automatically moves to the next instruction in the text segment unless a branch instruction changes the flow. To display codes at odd index positions, only one instruction needs to be modified. The instruction PNE T20 skip is changed to PEQ T20 skip. This small change demonstrates how branching conditions can alter program behavior efficiently. This output shows the security codes displayed based on even index positions. When the condition is changed, the output correctly displays codes at odd index positions. This confirms that the features works correctly as intended. The LW instruction is used to load array elements from memory. The ND instruction checks whether the index is even or odd. PQ and BNE control the program flow using branching. ID increments the index and memory address. Syscall handles input and output operations. In conclusion, this feature demonstrates how array indices can be used to filter and display selected data elements. It reinforces the understanding of loops, branching, registers, and memory addressing in MIPS assembly. This implementation successfully meets the objectives of the computer organization and architecture course.